Okay, I've covered a whole bunch of theory. Now what I'm going to do is do a few Olympiad questions just as examples. I'm just going to do them. And here's a genuine Olympiad question. I can't quite remember where it's from now, but anyway, let me just state it. Prove that no integers x and y satisfy x cubed plus y to the 4 equals 19 to the power 19. I can't remember if integers included positive and negative ones, but I think it was positive integers, but I can't quite, it doesn't matter for y of course, but for x it might be x cubed. And it makes a difference here because if it's positive integers, this is a finite equation, and so in principle you could just go through all the different versions or all the different possibilities of y and see if there's a corresponding x. I can't remember that. I can't remember if it was integers or positive integers. Anyway, how do we solve this? No integers satisfy, so it's not just a question of finding them. 19 to the power 19 is a very, very large number, of course. It's big number. Too big for your calculator to hold, anyway. We need to find some feature of this number that allows us to show that there's no such no solution. Well, what I'm going to do is write down Fermat's theorem. There's Fermat's theorem where P is prime and A and P are relatively prime. Given that, and you'll remember that we talked about primitive roots. We talked about the order of integers and so forth. Given Fermat's theorem, and given that we've got a power 3 and a power 4 here, and 3 times 4 equals 12, which is 13 minus 1, it would seem to make sense to consider this thing here, this equation modulo 13. That's just a heuristic. That's not governed by any mathematics. That's just what you might think. If you've got a cube plus a fourth power, then something interesting might happen modulo 13. So I guess the first thing to do is to work out the right-hand side. Well, it's 19 to the power 19 modulo 13. So if we do absolutely everything modulo 13, let's have a look at what happens. Well, that's equal to 6 to the power 19 modulo 13. Everything is going to be modulo 13 now. Everything. 6 to the power 19 is a lot easier to work out than 19 to the power 19. Well, let's work out some powers of 6 and see what happens. There's 6, 6 squared, 6 cubed, and so forth. So there's 6, that's 36, which equals 10, of course. So 6 cubed is equal to 60, which is modulo 30. Well, let's write down some times tables of 30. 26, 39, 52, 65, 78. That'll do. That'll do. So it's 8, isn't it? Because it's 52 plus 8. So 6 to the power 4 equals 6 eighths of 48, which is going to be 4. Not doing particularly well here. How about 6 to the power 8? Well, that equals 16, doesn't it? Which equals 3. 6 to the power 16 equals 9, which equals 9, I guess. The reason I say 6 to the power 8, because that 6 to the power 8 is 6 to the power 8 equals 6 to the power 4 squared, which equals 4 squared, which equals 16, which equals 3. Okay? So what we need to do is, it's 8 nines, isn't it? So 6 to the power 19 equals 6 to the power 16 times, sorry, start again, 6 to the power 16 times 6 cubed equals 9 times 8 equals 72. And having a look at this table here, that's equal to 7, isn't it? equals 7 modulo 30. So let's just, what have we done here? We've had a look at this equation here, and so modulo 30, if on this side is everything is modulo 13, we've got x cubed plus y to the 4 equals 7 modulo 13, which I don't need to say because it's up here. Do there exist such values? Well, let's work out what they are modulo 13, and then see if anything, see if we can conclude anything from that. Okay, well, let's see what we conclude. Well, let's write out what x and y might be. Oops, 2, 3. I'm going to write a space, aren't I? Let's try. Let's do it here. 0, 1, 2, 3, 4, 5, 6, 7. Call that n. N squared. That's going to be 0, 1, 4. That's going to be 9. It's going to be 3 because it's 16. That's 25, which is minus 1. Modulo 13. 6 is 36, which is 26 plus 10. 7 sevens are 49. Where's my table? Where's my table? 49 plus 3, isn't it? 8, 9, 10, 11, 12. 8 squared is 64. 7 eighths are 91. 64 is minus 1 modulo 13. 9 nines are 81. That's 3 again, isn't it? See the peculiar pattern here? So if I ask what's the square root of 3, we've got 3 answers here. Because 4 squared equals 7 squared equals 9 squared equals 3 modulo 13, which is quite interesting. Just note that. We'll just save that for later. 10 squared is 100, of course. That's 9 modulo 13. 11 squared is 121. Can I do anything with that? That's 91 plus 13 is 104. Oops. 104. And then it's 117, isn't it? So that's 4. That's 4. 11 squared is 4 modulo 13. 12 squared is 120. Sorry, it's 144. It equals 143 plus 1 equals 1. There you go. So there's my table of squares. Not entirely sure why I did that. Oh yes, I did, because I want to work out n cubed. So to get n cubed, I'm just going to multiply these columns together. 8, 3 nines are 27, 4 threes are minus 1, 5 is minus 5, which is 8. 60, what's 60? That's 8 as well. 7 threes are 21, which is 8 again. 8 times minus 1 is minus 8, which is 5. 9 threes are 27. 10 nines are 90. 11 fours are 44, so that's 5. 12 ones are 12. What can we conclude from that? That n cubed equals, well, it's n cubed is a member of the set 0 for this one, 1, minus 1, 8, or 5. Well, I guess you could say that's 0 plus or minus 1 or plus or minus 5. N cubed is in this set here, which is quite nice. That's quite a nice result. N to the 4. What I want to do is to square this column here. 1 squared is 1. 4 squared is 16. 9 squared is 81. Go back to my table. That's 3, isn't it? 3 threes are 9. Let's keep it as 9 for the moment. Or that is minus 4. 1. 10 squared is 100, which is 9. 3 squared is 9. Minus 1 squared. 3 threes are 9. 9 nines are 81. 4 fours are 16, and minus 1 squared is 1. So let's have a look at what we've got here. We've got, just pinch in a little bit, we've got n to the 4 is in the set either 0 or 1 or 3 or 9. Not as symmetrical as the n cubed, is it? I was trying to write it in a nice easy way like this, but I didn't manage to do that, because it's 0 or 1 or 3 or 9. And what was the n cubed? Now that was plus or minus. There we go. So what I'm going to do is see what I can get by adding one of these guys to one of these guys. So we've got 0 plus or minus 1 plus or minus 5 plus 0, 1, 3 or 9. And of course what I'm trying to do is to get 19 to the power 19, which I worked out, feels like a long time ago now, but I worked, oops, just a minute, feels like a long time ago, doesn't it? But there it is, 7. Can I get a 7 out of these guys here? Where are we? Can I get a 7 out of that? 0 plus or minus 1 plus or minus 5 plus 0, 1, 3 or 9. And if I can't get a 7, then I've proved it. Well, let's just start with the 9. If I start with the 9, then the 0 won't do, plus or minus 1 won't do, plus or minus 5 won't do. If I start with the 3, 0 won't do. To get to 7, I need to get to 7. That won't do. That's 8 or minus 2. If I start with the 1, that won't do. That's 0 or 2. No, and if I start with a 0, there isn't a 7 in there. How would I prove that in an Olympiad questionnaire? What I would do is this. I would make a little table of the answer of addition modulo 13, 0, 1, 3 and 9 to 0, plus 1, minus 1, plus 5 or minus 5. Well, 0 plus 1, minus 1, plus 5 and minus 5. 1, that would be 2 or 0. 1 plus 5 is 6, 1 minus 5 is minus 4. 3 plus 0 is 3, 3 plus 1 is 4, 2, 3 plus 5 is 8, 3 minus 5 is 10. 9 plus 0 is 9, 9 plus 1 is 10, 9 minus 1, 9 plus 5 is 14, 9 minus 5 is 4. So we know now that x cubed, sorry, that's x squared, isn't it? X cubed plus y to the 4 is a member of these sets here, 0, plus or minus 1, which we've got. Have we got a 3? We've got a 3, which is here. Oh, we've got a 2 as well, haven't we? We've got plus or minus 2 because we've got a 10 there as well. We've got a 3. What's minus 3 modulo 13? It's 10, isn't it? Plus or minus 3. Plus or minus 4 because I've got an 8 there. Plus or minus 5 because I've got them there. Or 6. Have I got a minus 6? Ah, well, minus 6 equals 7 modulo 13. And we know that 19 to the power 19 equals 7 modulo 13. And that's precisely the one that's missing because we have no minus 6. So, to prove the original question, which was up here, prove that there's no integers. Where is it? Prove that no integers x and y satisfy x cubed plus y to the 4 equals 19 to the power 19. Consider everything modulo 13, and then observe that the left-hand side can never be equal to 7, and the right-hand side is equal to 7. So that's it, QED. And I'm going to stop there. I think this has been a long one, but quite instructive.